The cosmos is a silent ocean of unanswered questions. We float on a tiny speck, surrounded by a darkness hiding secrets beyond our wildest imagination. This journey explores 25 of the universe's most profound mysteries, each one a frontier that challenges everything we think we know. You will discover hidden forces shaping reality and cosmic puzzles that defy all explanation. We will confront an invisible skeleton holding galaxies together and a signal from the void that lasted just 72 seconds. What could possibly cause a star to flicker so erratically that scientists considered alien engineering? Why does our map of the Big Bang's afterglow seem to have a preferred direction, a potential crack in the very foundation of modern cosmology? When you look up at the night sky, what single mystery do you most hope we will solve in your lifetime? Our story begins with the universe's greatest mystery, the event that set everything in motion. The Big Bang theory describes an explosive beginning from an infinitely hot and dense point, a singularity. From that initial state, space itself expanded, cooling over billions of years to form the galaxies and stars we see today. We can observe the afterglow of that primordial fireball, the cosmic microwave background, as firm evidence. Yet this powerful theory leads to an even more profound question, one that science struggles to answer. What came before the Big Bang? The very idea of a before challenges our understanding of time itself, for if time began with the Big Bang, then asking what happened before may be like asking what is north of the North Pole. Some physicists propose our universe emerged from a cosmic seed, a tiny speck of vacuum energy born from a random quantum fluctuation in a deeper, timeless void. In this view, our entire cosmos could be just one bubble in a vast, frothing multiverse, where new universes are constantly budding off from others. Another idea suggests a cyclic model, a perpetual cosmic heartbeat where our universe expands from a Big Bang only to eventually contract back into a big crunch, which then triggers the next Big Bang in an endless cycle. Could our reality be just one page in an infinite book of universes, each with its own unique laws of physics? This first mystery forces us to confront the very limits of our knowledge, peering into the abyss of our own origin story. But if the Big Bang set the cosmic stage, what is it built upon? Galaxies spin at speeds that should tear them apart, their outer stars whirling so fast that the visible matter alone could never provide enough gravity to hold them together. Something invisible, something we cannot see, must be providing the extra pull. This is the ghost in the cosmic machine, dark matter. Its presence is felt everywhere. We see its gravitational hand bending the light from distant galaxies, a phenomenon called gravitational lensing, where massive objects act like cosmic magnifying glasses. We map its distribution in the vast cosmic web, the intricate scaffolding upon which galaxies are hung. We know it is not made of the same protons, neutrons, and electrons that build our world. It does not absorb, reflect, or emit any form of light, making it completely transparent to our most powerful telescopes. It simply does not interact with light at all. Think of it like the wind. You cannot see the wind itself, but you can see leaves dancing in the street and feel its force against your skin. Dark matter is the cosmic wind, its existence undeniable through the motion of stars and the warping of space-time, yet its true nature remains utterly hidden. This invisible substance makes up about 85% of all the matter in the universe. Everything we can see, every star, every planet, every human being, is just the faintest visible frosting on a vast, dark cake. So what could it possibly be? The leading candidates are hypothetical particles that barely interact with normal matter. They could be WIMP or weakly interacting massive particles, trillions of which might be streaming through your body every second without a trace. Or they could be actions, particles so light and numerous they could form a pervasive cosmic fog. Decades of sensitive experiments deep underground have tried to catch a single one of these phantom particles, but so far the detectors have remained silent. The mystery only deepens. How can something so fundamental, the very skeleton of the cosmos, be so completely elusive to our detection? Yet the invisible hand of dark matter is not the only force shaping our cosmic destiny. Something far stranger is at work on the grandest scales, a force that does not pull the universe together, but actively rips it apart. In the late 1990s, two independent teams of astronomers made a shocking discovery. They were studying distant supernova, the titanic explosions of dying stars, to measure how fast the universe's expansion was slowing down due to gravity. Instead, they found the opposite. The expansion of the universe is not slowing at all, it is speeding up. Galaxies are flying away from each other faster and faster as time goes on. This revelation was so profound it earned the researchers the Nobel Prize and introduced the world to the universe's most dominant and most mysterious component, dark energy. This is not a force in the traditional sense like gravity or magnetism. Dark energy appears to be a property of space itself, a kind of anti-gravity woven into the fabric of the vacuum. Imagine space as the surface of a stretching rubber sheet. Dark energy is not an object on that sheet, but the sheet itself being stretched more and more rapidly, pushing every point away from every other point. While gravity works tirelessly to pull matter together, forming galaxies and stars, dark energy works on the vast, empty expanses between galactic clusters, causing the entire cosmic structure to fly apart. The numbers are staggering. Dark energy is thought to constitute about 68% of the total energy in the universe. All the matter we know, from planets to people, and all the dark matter we have yet to find, makes up less than a third of everything that exists. The rest is this enigmatic energy pushing the cosmos toward an unknown fate. So what could it be? The leading yet deeply unsettling explanation is the cosmological constant, an idea Albert Einstein first proposed and then famously called his greatest blunder. It represents a constant energy density filling all of space homogeneously. Another possibility is a dynamic energy field nicknamed quintessence, which could change over time. But these are just names for our ignorance. The true nature of dark energy remains one of the greatest puzzles in all of physics. Its implications are as profound as they are terrifying. If this accelerated expansion continues unchecked, dark energy dictates the ultimate fate of the cosmos, a fate known as the Big Freeze. In this distant future, galaxies beyond our own local group will eventually be pushed so far away that their light can no longer reach us. The universe will become a cold, dark, and lonely place, with islands of galaxies isolated in an ever-expanding, empty void. How do we reconcile a universe born from a single, violent expansion, now being torn apart by a force we cannot see or touch? So the universe is not only expanding, but that expansion is accelerating, driven by a mysterious dark energy. With hundreds of billions of galaxies, each containing hundreds of billions of stars, the sheer number of worlds where life could have arisen is beyond comprehension. The math seems to insist that we are not alone, that the cosmos should be teeming with civilizations. And yet, when we listen, we are met with a profound and unsettling silence. This is the heart of the Fermi Paradox, a contradiction first voiced by physicist Enrico Fermi in a simple, devastating question: where is everybody? If life is common, the galaxy is ancient, there has been more than enough time for an advanced civilization to arise and spread across the entire Milky Way, colonizing star after star over millions of years. Even moving at a small fraction of the speed of light, a spreading civilization could populate the galaxy in a cosmic blink of an eye. The evidence of their existence should be everywhere. We should see their engineering projects, their interstellar beacons, or the faint waste heat of their immense cities. Instead, we see nothing but natural phenomena. It is as if we have entered a library filled with countless books, every one of them blank. One chilling solution is the Great Filter hypothesis. This idea suggests that there is some kind of barrier, a near insurmountable challenge that prevents life from progressing to the stage of interstellar colonization. Perhaps the filter is behind us, something we have already passed, like the miraculous jump from non-living chemistry to self-replicating life. That would make us the first, a cosmic miracle. The far more terrifying possibility is that the filter lies ahead of us. It could be that almost every advanced civilization eventually discovers a technology that leads to its own destruction, whether through nuclear war, engineered plagues, or a runaway artificial intelligence. Our own silence could be a sign that no one makes it through this technological adolescence. Other solutions are less grim but equally strange. The zoo hypothesis proposes that advanced civilizations are out there, and they are aware of us, but they have chosen to deliberately avoid contact, perhaps to allow our species to develop naturally, like a galactic nature preserve. Or maybe the universe is just too big and the timescales are too vast. Civilizations could be blooming and dying like mayflies, their brief signals passing through the void at the exact wrong moments, missing each other by millennia. Perhaps they are communicating in ways we cannot yet perceive, using technologies based on physics we have not yet discovered. Or their greatest works are already in plain sight, disguised as natural astronomical phenomena, like the strange dimming of Boyajian star that some once thought could be an alien megastructure. The silence is not empty, it is a question. Are we alone because life is a fragile flame, easily snuffed out? Or are we simply not listening in the right way, in a universe that is far stranger and more wonderful than we have ever dared to dream? This cosmic silence is broken only by our own motion, a relentless pull toward an unseen destination. Our Milky Way galaxy is not sitting still. It is racing through the void at an astonishing 2 million kilometers per hour, drawn toward a mysterious region of space we call the Great Attractor. This is not a single object, but a colossal gravitational anomaly, a focal point of mass so immense it is tugging our entire galaxy and thousands of others along with it. The source of this pull lies in the direction of the constellation Centaurus, but for decades its true nature was hidden from our view. It sits directly behind the plane of our own galaxy, a region so choked with cosmic gas, dust, and the glare of countless stars that we call it the zone of avoidance. Trying to see the Great Attractor from Earth is like trying to see a distant mountain range through a thick, blinding fog. Our optical telescopes were useless, peering into a wall of obscurity. The breakthrough came when astronomers began using instruments that could see through the cosmic smog, radio and X-ray telescopes that revealed the hidden structures beyond. What they found was even grander than anyone suspected. The Great Attractor is not the ultimate source of the pull, but merely a waypoint on a much larger journey. We are being drawn toward an inconceivably vast concentration of mass known as the Laniakea supercluster. Laniakea, a Hawaiian word meaning immense heaven, is our cosmic home address, a web of 100,000 galaxies spanning 500 million light-years. Our Milky Way is just one galaxy on a suburban arm of this colossal structure, all of it flowing toward its gravitational center, a region dubbed the Norma cluster. So what could possibly possess enough gravity to command an entire supercluster? The leading theory points to an overwhelming concentration of dark matter, the invisible cosmic scaffolding, pulling normal matter along for the ride. It is a reminder that even on the grandest scales, we are still subject to the fundamental force of gravity, drawn toward a hidden heart in the darkness. What other immense structures lie beyond our current view, silently guiding the motion of the cosmos itself? Amidst this grand cosmic motion, the universe sometimes shouts. In 2007, astronomers sifting through old data found a spike of radio energy so powerful it defied belief. It lasted just 5 milliseconds, a blip shorter than a camera flash, yet in that instant it released more energy than the Sun emits in 80 years. This was the first detected fast radio burst, a blast of cosmic noise from billions of light-years away. These are not gentle signals, they are sonic booms from across the cosmos, brief and incredibly intense. For years, each new detection was a unique event, a single scream in the dark that left scientists scrambling for an explanation. Then came the repeater. In 2016, a source was found that did not just burst once, but again and again, sending out flashes in an unpredictable but undeniable pattern. This changed everything. The single bursts could be explained by catastrophic one-time events, the final death cries of stars being shredded by black holes or the collisions of incredibly dense neutron stars. But a repeater, something that survives its own outburst, pointed to an ongoing, powerful engine. What natural object could possibly produce such titanic, repeating bursts? The prime suspects are magnetars, a type of neutron star with a magnetic field so intense it could erase a credit strip from half the galaxy away. Think of a magnetar's crust under unimaginable strain, occasionally cracking and releasing a starquake, a seismic event so violent it ripples space-time and blasts out a pulse of radio waves we see as an FRB. Another theory involves a highly magnetic neutron star orbiting a massive, feeding black hole, with material being torn from the star and creating violent, periodic outbursts as it falls in. Yet the sheer power and bizarre patterns of some repeating bursts have led a few scientists to cautiously float another, far more speculative idea. Could some of these signals, especially the ones with precise, repeating rhythms, be evidence of artificial origin? Not necessarily a message, but perhaps the leakage from incredibly powerful technology. A civilization might use pulsed beams to drive interstellar light sails across the galaxy, their propulsion system appearing to us as a series of brilliant, repeating flashes. Or perhaps it is the result of cosmic engineering on a scale we can barely conceive. While most astronomers consider natural explanations far more likely, the mere possibility forces us to confront a profound question. If we were to find a signal that was unmistakably artificial, how would it change our place in the universe? These millisecond bursts are like cosmic Morse code, but we are still learning the alphabet, listening for a pattern in the static that might reveal whether we are hearing the death of stars or the birth of something else entirely. Pinpointing the source of a fast radio burst is like trying to find a single firefly in a pitch-black forest from 1,000 miles away. The blip is so brief, so fleeting, that by the time our telescopes register it, the show is already over. The true breakthrough came not just from detecting these bursts, but from catching them in the act with instruments sensitive enough to triangulate their origin. This requires a global network of radio dishes, a coordinated web of ears listening to the sky, ready to snap a celestial photograph the instant a flash goes off. When they succeed, the results are astonishing. One of the most famous repeating bursts was traced back to a small, faint, and unassuming dwarf galaxy over 3 billion light-years away. This was a crucial clue. Such a small galaxy lacks the heavy elements and the bustling stellar activity of a place like our Milky Way, suggesting that whatever creates these colossal explosions does not require a complex galactic environment. It points toward a source that can form even in the cosmic backwaters, something like a magnetar. Then, in our own galactic backyard, we witnessed a magnetar in the act. In April 2020, a magnetar within the Milky Way erupted, producing a radio blast that, while milder than its extragalactic cousins, confirmed their immense power. It was a smoking gun, proving that at least some fast radio bursts are born from these intensely magnetic stellar corpses. The process is thought to be a starquake, a sudden cracking of the neutron star's rigid crust under the strain of its own unimaginable magnetic field. This event releases pent-up energy in a shockwave that ripples outwards, accelerating particles and creating the brilliant flash of radio waves we detect. Yet the story is not so simple. Not all bursts lead back to such tidy explanations. Some appear to come from the halos of massive galaxies or from regions with no obvious stellar nurseries or recent cataclysms. This diversity of homes implies a diversity of causes. Perhaps there is not one single key to the mystery, but several. The repeater in the dwarf galaxy and the one off from our own magnetar suggest one pathway. But the single and never repeated bursts could still be the final, catastrophic death cries of stars, like a neutron star collapsing into a black hole or two ancient stellar remnants merging in a violent embrace. Each successful localization is a new piece of the puzzle, telling us not just where to look but what to look for. Are we hearing the birth pangs of new black holes or the tectonic groans of spinning magnets the size of a city? Each point on the map brings us closer to an answer, revealing a universe that is far more dynamic and explosive than we ever imagined. While listening for cosmic screams, we sometimes catch a whisper that defies all expectation. Far from the explosive power of fast radio bursts, a subtler mystery was unfolding around a single, average star 1,400 light-years away. Known as KIC 8462852 or Tabby star, it first made headlines not for what it emitted but for what it blocked. Citizen scientists with the Planet Hunters project, sifting through data from the Kepler Space Telescope, noticed its light curve was unlike anything ever seen. Instead of the regular, gentle dip of an orbiting planet, this star's light would plummet by up to 22% in chaotic, asymmetrical drops. The dimming was dramatic, irregular, and completely unprecedented, as if something colossal and strangely shaped was drifting in front of it. The most tantalizing and controversial hypothesis was that we were seeing evidence of an alien megastructure, a vast swarm of energy-collecting panels known as a Dyson sphere under construction, intermittently blocking the star's light. It was a moment where science fiction seemed to brush against science fact, capturing the world's imagination. Could this finally be the evidence we were not alone? The scientific community, of course, sought more grounded explanations. The first and most popular natural theory involved a vast, fragmented swarm of comets, stirred up by a passing star, creating a thick, dusty veil around Tabby's star. Others proposed the remnants of a shattered planet, creating a field of debris on a wildly eccentric orbit. The star itself was then studied in every wavelength of light, from ultraviolet to infrared. This is where the alien megastructure theory began to falter. A solid structure, like a giant array of panels, would block light equally at all wavelengths. But the dimming observed at Tabby's star was wavelength dependent, meaning some colors of light were blocked more than others. This pointed decisively toward dust, not solid metal or rock. Fine particles of dust scatter and absorb blue light more effectively than red light, creating a telltale signature that matched the observations perfectly. The final blow to the megastructure idea came with the star's long-term behavior. Over years of observation, Tabby's star was not just dipping erratically, it was also undergoing a slow, secular dimming. The overall brightness of the star was fading over time. This is not something a completed megastructure would do. It would block light consistently. Instead, it fit with a natural model of a star gradually being enshrouded by a colossal cloud of fine, circumstellar dust, likely the result of some recent catastrophic event in the system, like a planetary collision. So while the dream of a giant alien construction project faded, the reality is, in many ways, even more fascinating. Tabby's star is not evidence of aliens, but it is a profound reminder of how much we have yet to learn about the lives of stars and the chaotic processes that can shape planetary systems. It stands as a monument to scientific curiosity, a case where a wild, exciting idea was put to the test, and the truth, though less sensational, revealed a universe far more complex and unpredictable than we had imagined. What other mundane yet magnificent phenomena are we misinterpreting simply because we have never seen their like before? The universe is full of signals we struggle to explain, but few have ever captured our longing for contact like the WOW signal. It was a summer evening in 1977 at Ohio State University's Big Ear radio telescope. The instrument was slowly scanning the sky, listening for whispers from the cosmos when it recorded something extraordinary. A narrowband radio burst, 72 seconds of pure, intense signal that rose and fell exactly as a celestial source passing through the telescope's view should. It was so perfect, so textbook, that the volunteer astronomer Jerry Amon, upon reviewing the data printout, circled the alphanumeric sequence and wrote one word in the margin: "Wow." This was not a random blast of cosmic noise. It was a focused signal on a forbidden frequency, the hydrogen line at 1420 MHz, a quiet channel that scientists had long suggested would be an ideal calling card for an advanced civilization. It was the kind of signal we were hoping to find, and then it was gone. Decades of follow-up observations using more powerful telescopes have scanned that same patch of sky in the constellation Sagittarius thousands of times. The silence has been absolute, no repeat, no echo, nothing. So what was it? The search for a natural explanation has been just as fruitless. It could not have been a passing satellite or a reflection from space junk, as those would not have produced that clean, narrowband profile. A comet was once proposed, but its trajectory and the date did not match up. The signal came from a region of space with no known stars or planets at the time. It simply appeared, a 1-second hello from the void, and then vanished forever. Its legacy is profound. The WOW signal remains the strongest candidate ever for an artificial transmission from beyond our solar system, a fleeting moment where the silence of the universe seemed to break. It is a ghost in the machine of science, a reminder that the answer to our greatest question might have already called out to us, just once, leaving us to wonder for a lifetime what or who we might have heard. Deep in the silent expanse beyond the planets, two human-made pioneers were drifting off course. The Pioneer 10 and Pioneer 11 spacecraft, having completed their grand tours of the outer solar system, were on their way to interstellar space when tracking data revealed a subtle but persistent anomaly. They were slowing down. This was not the gentle tug of the sun's distant gravity, but an extra, tiny, and completely unexpected deceleration. A constant sunward push so faint it was like a gentle breath against a sail. For decades, this pioneer anomaly was a nagging whisper at the edge of physics. Was it some unknown drag from interstellar dust? Was it a flaw in our understanding of gravity itself? A hint that Einstein's theory needed a slight modification in the vast, empty reaches of the solar system? The mystery captivated scientists and enthusiasts alike, suggesting a fundamental secret waiting to be uncovered. The answer, when it finally came, was not written in the laws of new physics, but in the simple, mundane reality of heat. Researchers performed a breathtaking feat of digital archaeology, recovering old design documents and telemetry data to create a complex thermal model of the aging probes. They discovered the culprit was the spacecraft themselves. The nuclear power sources on board generated heat, which was radiated away from the spacecraft's surface. But this radiation was not perfectly symmetrical. A little more heat was emitted from the back of the dish-shaped spacecraft, pushing gently against their direction of travel, like the faint recoil from a warm light bulb. This thermal recoil force was the gentle push from nowhere, a phantom force born from their own warmth. The Pioneer anomaly stands as a profound lesson in cosmic mystery. It reminds us that the universe does not always reveal its secrets through grand cataclysms or alien signals. Sometimes the greatest puzzles are hidden in the smallest details, and the answer is not a revolution, but a meticulous, patient uncovering of the truth. It teaches us humility, showing that even the faintest whisper can lead us on a decades-long quest, and that the most satisfying solution often lies not in rewriting the laws of physics, but in understanding the intricate engineering of our own creations. What other subtle anomalies are we measuring right now, their true explanations still waiting in the data? Even the most disciplined scientific minds can be unsettled by a mystery that defies common sense. Albert Einstein famously dismissed a particular quantum phenomenon as spooky action at a distance, a phrase that perfectly captures its unnerving strangeness. This is the world of quantum entanglement, a deeply bizarre connection where two particles become inextricably linked, their fates intertwined no matter how far apart they are separated. Create a pair of these entangled particles, send one to the opposite side of the lab, or even to the other side of the galaxy, and a measurement performed on one will instantly influence the state of its partner. If you find one particle spinning up, its twin will be spinning down, a correlation that happens immediately, seemingly faster than the speed of light. For Einstein, this was an unacceptable violation of the cosmic speed limit he had established, a ghostly communication that made a mockery of local reality. He believed there must be some hidden variables, some unseen instruction manual carried by each particle that predetermined their behavior, preserving a sane and causal universe. For decades, this was a philosophical debate, a battle of interpretations between giants of physics. Then, in the late 20th century, technology caught up with theory. A physicist named John Bell devised a clever mathematical test to distinguish between hidden variables and true spooky action. When experiments were finally performed, the results were clear and shocking. Einstein was wrong. The particles were not following a pre-written script. There were no hidden variables. The connection was real and it was instantaneous. This leaves us with a profound and mind-bending question. How can two particles communicate faster than light, seemingly breaking a fundamental rule of the universe? The answer is both simple and deeply strange. They are not communicating at all. The prevailing interpretation is that the two entangled particles are not two separate entities, but a single quantum system. While they may be separated by vast stretches of space, in the quantum realm they effectively occupy the same reality. Measuring one particle doesn't send a signal to the other. It simply defines the state of the entire non-local system at once. It is as if you had a pair of magical gloves. You put one glove in a box and ship it to a distant star without looking inside. The moment you open your box on Earth and find a left-handed glove, you know with absolute certainty that the glove on that distant star is the right-handed one. The information about which was which didn't travel. It was inherent in the connected system all along. This has staggering implications for our understanding of reality itself. It suggests that the universe at its most fundamental level is not local, that objects we consider separate are, in some mysterious way, still connected. The very fabric of space and time may be a secondary structure emerging from a deeper, more entangled quantum reality. While this spooky action cannot be used to send meaningful information faster than light, preventing any possibility of a galactic telephone, it is the foundation for revolutionary technologies. Quantum computers leverage entanglement to perform calculations that would take classical computers billions of years, and quantum cryptography uses it to create theoretically unbreakable codes. The universe, it seems, is not just stranger than we imagine, but stranger than we can imagine, with its most basic components woven together by invisible threads that ignore the distance between stars. This spooky connection hints at a universe far stranger than it appears, but what happens when reality faces its ultimate shredder? A black hole presents a terrifying puzzle, not just for anything that falls in, but for the fundamental laws of physics themselves. Stephen Hawking made a stunning prediction that black holes are not completely black. Thanks to quantum effects at their boundary, they slowly leak radiation and evaporate over astronomical time scales. This Hawking radiation, however, carries a terrible price. It is purely thermal, random noise that contains no information about the material that formed the black hole or whatever unfortunate stars and planets have since fallen in. When the black hole finally evaporates and vanishes, all that intricate information about the properties of every atom, every particle, is seemingly erased from the universe forever. This creates the black hole information paradox, a direct conflict between the two pillars of modern physics. General relativity, which governs black holes, says the information is lost inside the singularity and gone for good. But quantum mechanics has a sacred, unbreakable rule: information cannot be created or destroyed. It can be scrambled, hidden, or made incredibly difficult to read, but it must be preserved. You can burn a book and turn it into ash and smoke, but in principle, if you could track every particle and measure every quantum state of that smoke, you could reverse the process and reconstruct the book. Hawking's calculation suggested that black holes are the one exception, a cosmic furnace that burns the book so completely that not even the ghost of a single letter remains. This idea was so unsettling that physicists, including Hawking himself, wrestled with it for decades. How could the universe allow such a fundamental law to be broken? The solution, it seems, requires rethinking the nature of reality itself. One leading idea is the holographic principle. This astonishing concept suggests that all the information about everything within a volume of space can be encoded on its boundary, its outer surface. For a black hole, this means the information of every object that falls in is not lost inside, but is smeared and stored in a scrambled, two-dimensional form on the event horizon, the point of no return. The three-dimensional reality we perceive is like a holographic projection from that two-dimensional surface. As the black hole evaporates via Hawking radiation, this information is slowly and chaotically leaked back out into the universe. It is not lost, just transformed into the most complex puzzle imaginable. Another, more violent solution is the firewall hypothesis. It proposes that the event horizon is not the smooth gateway we once thought. Instead of falling gently into the unknown, an astronaut crossing the horizon would immediately be incinerated by a wall of unimaginably high energy, a firewall. This firewall would be created by the immense strain of encoding the information of infalling matter onto the horizon, effectively burning it up and preserving the information in the resulting radiation. It is a drastic fix, saving the laws of quantum mechanics by turning the black hole's edge into a destructive inferno. These are not just abstract ideas, they force us to confront what we mean by space, time, and information. Is our three-dimensional world an illusion, a hologram born from a deeper, two-dimensional reality? Or is the universe protected by cosmic firewalls that prevent any deep exploration of its most extreme environments? The information paradox is not a minor technicality. It is a profound clue that our current theories are incomplete, pointing toward a deeper truth where gravity and quantum mechanics finally unite. What other cosmic rules have we misunderstood, waiting to be revealed in the heart of darkness? Yet the smooth cosmic backdrop we rely on might itself be an illusion. Our most pristine map of the infant universe comes from the cosmic microwave background, the faint afterglow of the Big Bang. This radiation is the oldest light we can see, a snapshot of the cosmos when it was just 380,000 years old. For decades, the CMB has been the ultimate proof of the cosmological principle, the idea that on the largest scales, the universe is homogeneous and isotropic. It should look the same in every direction, with no center, no edge, and no preferred axis. But when scientists created exquisitely detailed maps of this primordial light, they found something that sent a chill through the world of cosmology, an anomaly so unnerving they nicknamed it the axis of evil. The name is deliberately provocative, hinting at a flaw that could undermine our entire cosmic worldview. The anomaly is not a single feature, but a strange alignment of several. The temperature fluctuations in the CMB, the hot and cold spots that are the seeds of all future galaxies, appear to be aligned along a particular plane in the sky. Even more strangely, the plane of our own solar system seems to be aligned with this cosmic axis. This is deeply unsettling. Why would the universe in its infancy, long before the Sun and Earth even existed, share an orientation with our local celestial neighborhood? It is as if you found the fossil of a prehistoric creature and its bones were arranged to spell out your own name. The simplest explanation is that this is a colossal coincidence, a statistical fluke that looks significant only because we are the ones looking at it. Or more worryingly, it could be a systematic error, a subtle contamination from our own galaxy's light, or an artifact of the way we process the data. But after years of analysis with increasingly sophisticated satellites, the peculiar alignments have stubbornly refused to go away. If they are real, the implications are profound. A preferred direction in the cosmos would shatter the cosmological principle. Our universe would not be smooth and featureless on the grandest scales. It would have a structure, a grain like wood, with a direction in which the laws of physics might subtly change. Could our universe be but one bubble in a vast multiverse, and this axis is a bruise left from a collision with another cosmic bubble in the distant past? Or does it point towards something even more exotic, a relic of the conditions that existed before the Big Bang, a fingerprint of a deeper reality imprinted on our own? The axis of evil remains an open wound in our standard model of cosmology, a quiet but persistent signal that the universe may be keeping one of its biggest secrets hidden in plain sight, written in the very first light it ever produced. This fundamental crack in our cosmic map is written in the light of the oldest stars. When the universe was just a few minutes old, a frenetic burst of nuclear fusion forged the first atomic nuclei in a process called Big Bang nucleosynthesis. The models for this primordial cookbook are exquisitely precise, predicting how much hydrogen, helium, and a tiny trace of lithium should have been created. For hydrogen and helium, the predictions match the observed abundances in ancient stellar atmospheres almost perfectly, but for lithium, the numbers are catastrophically wrong. The oldest stars in our galaxy contain only about 1/3 of the lithium that the Big Bang theory says should be there. It is as if we found a perfectly preserved recipe from the dawn of time, followed it exactly, and yet one key ingredient consistently went missing from the final dish. This is the lithium problem, a small number with massive implications. Where did it go? One possibility is that our understanding of stellar physics is incomplete. Could these ancient stars be churning their outer layers, dragging lithium down to their hot interiors where it is destroyed? Some models suggest a slow, steady burning of lithium over billions of years, a kind of cosmic digestion that depletes the original supply. Yet this seems insufficient to account for the entire discrepancy. Another, more radical idea points to new physics in the early universe. Perhaps an unknown particle, like a relic from supersymmetry, was present in those first few minutes, interacting with nuclear reactions and subtly altering the outcome, suppressing the creation of lithium. Or maybe our understanding of nuclear cross-sections, the probabilities of particles fusing together, is slightly off for a key reaction that produced or destroyed lithium. The most profound possibility is that we are misreading the data entirely. What if the primordial lithium abundance is actually correct, and the ancient stars we use as cosmic fossils have somehow been enriched or altered in a way we do not yet comprehend? This missing lithium is a ghost in the machine of creation, a quiet anomaly that whispers of processes we have not yet imagined, hidden within the first 3 minutes of everything. A silent traveler from a distant star slipped through our solar system in 2017. It was the first object ever detected from interstellar space, and astronomers named it Oumuamua, a Hawaiian word for scout. This visitor was unlike anything we had ever seen. Its trajectory was hyperbolic, meaning it was not bound by the sun's gravity, simply passing through on a one-way journey from the unknown into the unknown. But its strangeness only deepened with every observation. First, there was its shape. Based on the extreme variations in its brightness, Oumuamua appeared to be highly elongated, perhaps 10 times as long as it was wide, a tumbling cosmic cigar tumbling through the void. Natural solar system objects like asteroids and comets are typically lumpy and potato-like. Nothing we have ever seen resembles this strange, needle-like form. Then came the most baffling behavior of all, its acceleration. As Oumuamua sped away from the sun, its path could not be explained by gravity alone. It was ever so slightly speeding up, as if being pushed by an unseen force. This is common for comets, as ices on their surface heat up and vent gas, forming a tail that acts like a rocket engine. Yet when astronomers pointed their most powerful telescopes at Oumuamua, they saw no coma, no tail, no cloud of gas or dust whatsoever. It was completely inert, a dark, silent rock exhibiting the push of a comet without any of the usual evidence. This non-gravitational acceleration sent the scientific community into a frenzy of theories. The leading natural explanation proposes that Oumuamua was a chunk of solid nitrogen ice, a kind of cosmic iceberg. As it passed close to the sun, the nitrogen would have sublimated, turning directly from a solid to a gas, providing the gentle thrust without creating a visible dusty tail. This could also explain its unusual shape, as such an object might erode into a flat, pancake-like slab that would appear elongated from certain viewing angles. Other ideas suggest it was a dust bunny, a fragile aggregate of materials so porous and light that radiation pressure from the sun itself could have pushed it along. But the mystery was so profound that it opened the door to more speculative possibilities. Could Oumuamua have been a piece of alien technology? The possibility, however remote, was raised by Harvard astronomer Avi Loeb, who suggested it might be a light sail, a thin, manufactured object pushed by the radiation pressure of starlight. Its unusual shape and unexplained acceleration, while not proof, were consistent with what such an artificial object might look like. The debate was intense, pitting conventional astronomy against a radical, thrilling hypothesis. The truth is, we may never know for certain. Oumuamua is now far beyond the reach of our telescopes, a fleeting enigma that visited our cosmic neighborhood for just a few short months before disappearing back into the dark. It serves as a humbling reminder that the universe is capable of producing wonders we have never dreamed of, and that our first contact with another star system may not have been a deliberate message, but simply a piece of cosmic driftwood washing up on our shore for a single, mysterious moment. Far beyond the orbit of Neptune lies a frozen frontier, a vast donut of icy worlds known as the Kuiper Belt. This is the solar system's attic, filled with remnants from its violent birth. But as our telescopes probed deeper into this distant realm, they discovered something deeply puzzling. The number of objects does not gradually thin out into the emptiness of interstellar space. Instead, it plummets. There is a sharp and absolute edge, a cliff beyond which the frozen debris field simply stops. This Kuiper Belt cliff is a boundary that should not exist. In a system that formed from a swirling, continuous disk of gas and dust, we would expect a gentle fading, a slow dissipation of material. The sudden absence is like walking through a dense forest and stepping through an invisible wall into a barren desert. What could have carved such a clean, dramatic edge in our cosmic backyard? The most tantalizing theory points to the gravitational hand of an unseen giant. Astronomers have long speculated about a possible Planet 9, a world several times the mass of Earth orbiting far beyond Pluto. The gravitational pull of such a hidden planet could have shepherded the Kuiper Belt objects, sweeping them up or hurling them inward, leaving behind a stark, truncated border. Its influence would act like a cosmic shepherd, corralling the icy bodies and creating a sharp edge at the outer limit of its domain. We see hints of this shepherd's work in the strange, clustered orbits of some of the most distant objects, all swinging around the Sun in a peculiar alignment that suggests a common, massive perturber. Yet after years of searching, this hypothetical world remains elusive, a ghost in the data. Another possibility reaches back into the solar system's violent infancy. Perhaps this cliff is a fossil, a relic of the protoplanetary disk from which our planets formed. The original cloud of material that coalesced into our Sun and its planets may have had its own natural edge, a cut-off point where the density of dust and ice dropped precipitously. The Kuiper Belt Cliff would then be a preserved snapshot of that primordial boundary, a fossilized shoreline from the dawn of our solar system. Or the answer could be even more dynamic. Maybe our Sun did not form in isolation. It was born in a stellar nursery surrounded by thousands of other sibling stars. A close pass from one of these siblings in that chaotic early era could have stripped away the outer material of our Kuiper Belt, gravitationally plucking the most distant objects and stealing them away, leaving behind the cliff we see today. Each explanation paints a different picture of our cosmic history. Is the cliff the signature of a hidden world still waiting to be found, the frozen echo of our system's birth, or a scar from a long-lost stellar encounter? This silent boundary in the deep freeze challenges our understanding of how solar systems are built and what secrets might still be lurking in the darkness just beyond our sight. Our most trusted cosmic measurements have begun to disagree, revealing a crack in the very foundation of modern cosmology. This is the Hubble tension, a stubborn and growing discrepancy in one of the most fundamental numbers in the universe, the Hubble constant. This constant tells us how fast the cosmos is expanding today, the current rate at which galaxies are flying apart. For decades, we have worked to pin down this number with ever greater precision. But now two of our most reliable methods are giving us different answers, and the gap is only widening. One path to measuring the Hubble constant is to build a cosmic distance ladder. Astronomers use nearby stars whose distances we can measure directly to calibrate the brightness of more distant stars, which in turn helps us gauge the distances to entire galaxies. By observing how fast those galaxies are receding from us, we can calculate the expansion rate. This method, using tools like the Hubble Space Telescope, gives us one clear number. Yet when we use the universe's baby picture, the cosmic microwave background, we get a different result. The CMB allows us to extrapolate forward from the infant universe to predict what the expansion rate should be today, based on our best model of cosmology. The problem is, the universe's current expansion rate measured by the distance ladder is significantly faster than the rate predicted by the ancient light. It is as if you used a child's birth weight to predict how heavy they would be as an adult, only to find they grew up to be much larger than your model ever allowed. This is not a small statistical fluke. The uncertainty in both measurements has shrunk, yet the values refuse to converge. This tension could mean one of two things. Perhaps there is an unaccounted for systematic error, a subtle miscalibration in one of our intricate measurement chains that we have not yet discovered. But many scientists are starting to believe the more exciting possibility that this is a real clue pointing toward new physics. Our standard model of cosmology, which includes dark matter and dark energy, might be incomplete. Maybe dark energy is not a constant but an evolving force that has changed over time, accelerating the expansion in a way we did not anticipate. Or perhaps there is a new type of neutrino or some other exotic particle from the early universe that subtly altered the expansion history. The Hubble tension is a quiet crisis, a fundamental disagreement at the heart of our understanding of the cosmos. It forces us to ask whether we have mapped the universe correctly, or if we are on the verge of a revolution that will reveal a cosmos even stranger than we thought. Why does the universe remember the past but not the future? This simple question hides one of the most profound puzzles in all of physics, the nature of time itself. We feel time flowing in one direction, an irreversible current from what was to what will be. You can turn an egg into an omelette, but you cannot turn an omelette back into an egg. This one-way street is known as time's arrow, and its pointer seems to be rooted in a concept called entropy. Entropy is essentially a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. The universe as a whole is moving from a state of lower entropy, an ordered and compact beginning at the Big Bang, toward a state of maximum entropy, a final, uniform heat death where energy is evenly distributed and nothing ever happens again. This relentless slide into disorder gives us the thermodynamic arrow of time. It explains why heat flows from hot to cold, why ice melts in a warm room, and why memories are only of the past. Our very ability to remember yesterday but not tomorrow is tied to this cosmic increase in messiness. Yet this explanation only pushes the mystery one step further. Why was the entropy of the early universe so incredibly low to begin with? What set the cosmic clock ticking with such a finely tuned, ordered initial state? Some physicists suggest that our universe is just one bubble in a vast multiverse, and we simply happen to live in a rare bubble where the conditions allowed for a low entropy beginning, making our perception of time's flow a kind of cosmic accident. Others wonder if the arrow of time is somehow linked to the ongoing expansion of the universe. As space stretches, it creates more room for disorder to increase, weaving the forward march of time directly into the fabric of the cosmos. But then there is the psychological arrow of time, our own internal experience of a flowing present. Why do we perceive a now that constantly moves forward? Is this a direct consequence of our brain's thermodynamics, a biological process driven by the same increase in entropy that governs the universe? Or does consciousness itself play a role in creating the illusion of passage, a question that straddles the line between physics and philosophy? The laws of physics themselves, at their most fundamental level, are almost entirely time-symmetric. The equations that govern particles work just as well running forward as they do backward. This means that a universe with time flowing in reverse is, in principle, perfectly possible according to the math. Yet we live in a world where that is not our reality. Something at some point broke this symmetry and gave us the irreversible world we know. The mystery of time's arrow forces us to confront the very origin of our cosmic order. Is the flow of time a fundamental property of the universe, or is it merely an emergent illusion, a side effect of our particular journey from order to chaos, a story written in the increasing disorder of everything around us? Between the great walls and filaments of the cosmic web, the universe holds its breath. Stretching for hundreds of millions of light years are regions of terrifying emptiness, voids so vast they could swallow thousands of galaxies without a trace. The most famous of these is the Boötes void, a spherical chasm of near nothingness so large that if our Milky Way sat at its center, we would have had no knowledge of other galaxies until the 1960s. This is not merely empty space, it is a cosmic desert on a scale that defies easy explanation. In a universe that is supposed to be broadly uniform, these voids are staggering anomalies. How can an area so immense contain so little? The leading theory suggests they are a natural outcome of gravity's work over billions of years. As matter began to clump together in the early universe, forming the seeds of galaxies and clusters, it also left behind great empty bubbles. Think of a foam of soap suds where the walls of the bubbles are dense with galaxies, but the interior of each bubble is a vast, empty chamber. Gravity amplifies this over time, pulling even more matter from the voids into the filaments and nodes, making the rich regions richer and the poor regions poorer. Yet the Boötes void is so disproportionately empty that it challenges even this model. It should contain tens of thousands of galaxies based on the average distribution of matter, but instead, only a few dozen have been found drifting in this colossal darkness. One possibility is that multiple smaller voids have merged over time, like soap bubbles coalescing into one giant cavity. Another, more speculative idea is that something in the very early universe created a primordial defect, a giant scar in the fabric of space-time that prevented matter from ever gathering there. The existence of these voids forces us to reconsider the universe's architecture. They are not simply blank spaces, they are active players in cosmic evolution. The expansion of space itself accelerates within these voids, as the feeble gravity of their scant contents cannot fight back against dark energy's push. A galaxy inside a void will find itself being pulled away from its neighbors faster than a galaxy in a crowded cluster, isolated not just by space, but by the very dynamics of the cosmos. These great nothingnesses are a fundamental part of the cosmic web, the dark counterpoints to the bright nodes where galaxies swarm. Their immense scale and profound emptiness ask a haunting question. Are we living in an unusually dense neighborhood, looking out at the void, or is our vibrant galactic cluster the true anomaly in a universe that is, for the most part, a silent and endless expanse of nothing? Even the vacuum of space is not truly empty. It seethes with a faint quantum energy, a sea of virtual particles that constantly flicker in and out of existence. But what if your own motion could change this fundamental nature of reality? The Unruh effect proposes exactly that, a bizarre prediction of quantum field theory where an accelerating observer would perceive warmth and light in what a stationary person sees as an utter void. Imagine you are floating in the darkness of deep space, perfectly weightless and still. To you, the universe is cold and black, a perfect vacuum. Now, imagine you fire your rockets and begin to accelerate faster and faster. According to the theory, you would no longer be surrounded by emptiness. You would instead find yourself bathed in a faint, warm glow of radiation, a heat bath of real particles popping into existence all around you. This is not an illusion, but a direct consequence of your acceleration warping your perception of the quantum fields that fill the universe. The faster you accelerate, the warmer this phantom glow would feel. For a human astronaut, the acceleration required to produce even a tiny fraction of a degree of heat would be unimaginably vast, far beyond what any living organism could survive. The temperature is so faint for any realistic acceleration that it remains completely undetectable with our current technology. Yet the implications of this effect are profound, shaking our understanding of what is real. It tells us that the very concept of a particle is not absolute, but depends entirely on the state of motion of the observer. One person's vacuum is another person's furnace. This strange idea is deeply intertwined with Hawking radiation from black holes. The intense gravity at the event horizon creates a similar effect, with one observer falling in and seeing nothing, while a distant stationary observer sees the black hole glowing with heat. The Unruh effect suggests that acceleration and gravity are, in a deep sense, equivalent, not just in the way Einstein taught us, but in how they conjure particles from the seemingly empty fabric of space. How can we ever test such a strange prediction? The challenge is immense, as creating the necessary accelerations in a lab is currently impossible. Some physicists propose using intense lasers or other exotic setups to simulate the conditions indirectly, searching for the faintest whispers of this acceleration-induced reality. The Unruh effect forces us to ask, is the universe we perceive nothing more than a reflection of our own motion? Are the particles we count as real merely phantoms, dependent entirely on our path through the cosmos? Deep within the heart of our galaxy, a mysterious and persistent glow defies easy explanation. This is the galactic center excess, an unexpected surplus of high-energy gamma-ray radiation that floods from the Milky Way's core. It is a brilliant, diffuse light that should not be there, or at least not in such abundance. When scientists meticulously subtracted all the known sources of gamma rays, from pulsars to stellar remnants, a bright and puzzling excess remained shining from the darkness. The heart of our galaxy is not just a place of ancient stars and a supermassive black hole. It is the source of a cosmic question written in pure energy. What incredible engine could be powering this relentless, unidentified glow? Two compelling and utterly different theories have emerged to explain it. The first possibility is as profound as it is elusive: dark matter. The center of the galaxy is thought to be densely packed with this invisible substance, the very cosmic scaffolding that holds everything together. If dark matter is made of particles, as many physicists believe, then those particles could be their own antimatter opposites. Where they meet and collide, they would annihilate each other in a flash of energy, producing the very gamma rays we see. In this scenario, the glow is the final death cry of the universe's most mysterious material, a continuous, faint fire burning in the galactic core. It would be the first indirect detection of dark matter, a monumental discovery revealing the true nature of most of the matter in the cosmos. The second possibility brings us back to the realm of more conventional, yet still spectacular, astrophysics. The galactic center is a crowded, chaotic place teeming with stellar activity. This glow could simply be the combined light of thousands of unresolved pulsars, the rapidly spinning corpses of dead stars. These cosmic lighthouses beam out intense radiation, and a dense, unseen population of them could easily create the observed excess. It would be like seeing the diffuse light of a distant city at night. From afar, it appears as a single, uniform glow, but up close, it resolves into millions of individual streetlights and windows. The challenge for astronomers is that our current telescopes cannot distinguish between these two possibilities. The glow is too smooth and too distant to pick out individual point sources. So the debate continues, a high-stakes scientific standoff. Is the galactic center excess the signature of a fundamental new particle, or is it just the collective hum of stellar engines we have not yet resolved? The answer lies in the heart of our own galaxy, a place of both creation and mystery, holding a secret that could either illuminate the dark or reveal a universe of hidden stars. Far from the galactic core's brilliant chaos, a dying star has painted a perfect geometric shape upon the cosmic canvas. The red rectangle nebula is an astronomical marvel, a structure so symmetrical it defies the usual chaotic beauty of stellar death. At its heart lies a binary star system, two aging suns locked in a gravitational dance. As one of them nears the end of its life, it has begun to shed its outer layers in a series of gentle, rhythmic pulses. This expelled gas and dust do not billow out in a random sphere. Instead, they are funneled into two vast, cone-shaped lobes by the intense winds and gravitational influence of the companion star. From our vantage point on Earth, we look directly down the barrel of these cones, their edges appearing to form a near-perfect X, a crimson cross in the darkness. The stunning red color itself is a clue to a deeper mystery, caused by a class of complex organic molecules known as polycyclic aromatic hydrocarbons. These are not signs of life, but rather the building blocks of soot, vast carbon-rich compounds that fluoresce with a deep red glow under the ultraviolet light from the dying stars. This nebula is more than just a pretty picture, it is a cosmic laboratory. Its sharp geometry reveals the profound order that can emerge from complex gravitational and hydrodynamic forces. The precise shaping shows how a binary companion can act like a sculptor's tool, carving chaos into an intricate, temporary work of art. The presence of those complex molecules is equally significant. It demonstrates that the late stages of stellar evolution are chemical factories, forging the very ingredients that could one day be incorporated into new planetary systems, and perhaps one day into the chemistry of life itself. The red rectangle nebula offers a glimpse into a strangely orderly death, a stellar farewell that leaves behind not just a cloud, but a legacy of structure and complex chemistry written across the void. A perfect geometric storm rages at Saturn's North Pole, a hexagon of clouds large enough to swallow 4 Earths. This six-sided jet stream has been churning for decades, perhaps even centuries, a permanent fixture in the gas giant's turbulent atmosphere. It is a work of art etched by physics, a puzzle that challenges our understanding of how weather works on a planetary scale. How can a storm, a phenomenon we associate with chaos, lock itself into such a rigid mathematical shape and persist for a human lifetime? The secret lies not in solid structures, but in the behavior of fluids moving at different speeds. Imagine a simple experiment with a spinning jar of water. If you place a small dye tracer in the center and spin the jar, the dye will spread into a circle. But if you create a difference in rotation speed between the center and the outer edge, something remarkable happens. The fluid can spontaneously organize into stable polygons, squares, triangles, and yes, even hexagons. This is the heart of the Saturn hexagon, a massive natural laboratory of fluid dynamics. The hexagon is essentially a meandering jet stream, a river of air screaming along at over 300 miles per hour. The stability of its six sides comes from the interaction between this fast-moving stream and the slower-moving atmosphere inside and outside its boundary. It is a self-organizing system where the energy of the storm carves and maintains its own crystalline walls. This is not a static shape, but a standing wave pattern, like a vibration frozen in the atmosphere. Think of it as a cosmic version of the music that can make a Chladni plate form intricate patterns in sand. Saturn's roaring winds are the music, and the clouds are the sand, arranging themselves into this persistent six-sided note. The sheer longevity of the hexagon is another part of its mystery. On Earth, our weather systems are fleeting, disrupted by continents, oceans, and the uneven heating of the sun. But Saturn is a smooth, fluid ball of gas with no solid surface to break the flow. Once a pattern like this establishes itself on such a vast scale, there is very little to disturb it, allowing the hexagon to become a semi-permanent feature of the planet's North Pole. This bizarre storm is more than just a celestial curiosity, it is a teaching tool. By studying it, we learn about the fundamental principles that govern all fluid systems, from the weather on our own world to the raging atmospheres of distant gas giants we cannot yet visit. The Saturn hexagon shows us that order can emerge from chaos, and that the universe often holds its most profound lessons in the most unexpected and beautiful places. Our cosmic map of creation holds a blemish, a patch of cold so vast and profound it might be a scar from a reality beyond our own. This is the CMB cold spot, a colossal region in the afterglow of the Big Bang where the temperature dips dramatically lower than the surrounding sky. It is not a small imperfection, but a sprawling area nearly 1 billion light-years across, a cosmic void of heat in the universe's first light. Such a feature should be incredibly rare in our standard model of cosmology, a statistical outlier that pushes the boundaries of chance. How could a random fluctuation grow to such an immense size? The most straightforward explanation is a supervoid, an enormous bubble of relative nothingness in the cosmic web. If this region of space contains far fewer galaxies and clusters than average, its emptiness could cause the cooling we observe. As light from the cosmic microwave background travels through a void, it must climb out of a gravitational well. Since gravity in a void is weaker, the light loses less energy on its journey out, a phenomenon known as the integrated Sachs-Wolf effect. This loss of energy would manifest as a slight cooling in the CMB, creating a cold spot. It is a cosmic optical illusion, a shadow cast by a great nothing. Yet when astronomers searched for this proposed supervoid, the results were ambiguous. While some studies found an underdensity of galaxies in that direction, it does not appear large or empty enough to fully account for the profound cold we see. The void is there, but it seems too shallow to cast such a deep shadow. This mismatch between the expected cause and the observed effect has opened the door to truly exotic possibilities. The most breathtaking is the idea that the cold spot is a bruise, a cosmic imprint left by a collision with another universe in the vast multiverse. In this mind-bending scenario, our universe is one bubble in a frothing sea of infinite realities. If another bubble universe brushed against our own during its inflationary phase, the energy released at the boundary of that collision could have created a localized region of cooler temperature, a permanent scar on the fabric of our cosmos. This would be the first observational evidence for a reality beyond our own, a tangible fingerprint of the multiverse. The evidence remains inconclusive, a tense standoff between the mundane and the magnificent. Is the cold spot merely a rare but natural cosmic emptiness, its true depth still eluding our measurements? Or are we staring at the first evidence of a sister universe, a silent witness to a collision of realities in the first moments of time? The answer lies in that faint, cold patch on the oldest map we possess, a reminder that our universe might not be alone, but simply one room in an infinite and sometimes crowded cosmic mansion. Deep beneath the Antarctic ice, a telescope is hunting for ghosts. It is not looking for light, but for the faint, telltale flashes created when a cosmic phantom, a high-energy neutrino, passes straight through our planet. These are the universe's most elusive travelers, born in the most violent events imaginable. A single neutrino can carry more energy than a major league fastball, all packed into a subatomic particle so tiny it can fly through a light year of solid lead without a single interaction. They are the universe's silent messengers, and they bring news from places light cannot escape. For decades, their origins were a perfect mystery. They would slam into our detectors from random directions in the sky, but by the time we registered the impact, their point of origin was lost. Tracing them back was like finding a single, specific raindrop in a hurricane, knowing it fell from a particular cloud 10,000 miles away. The challenge is that neutrinos have no charge and almost no mass, so they fly in perfectly straight lines, completely ignoring the magnetic fields that bend the paths of other cosmic rays. This makes them perfect cosmic pointers, but only if we can catch them with precision. The Ice Cube Neutrino Observatory solved this by turning a cubic kilometer of pristine Antarctic ice into a giant detector. When a rare neutrino does interact with an atom in the ice, it creates a faint blue glow that sensors can capture, allowing scientists to reconstruct its incoming direction and energy. The real breakthrough came when one of these ghostly particles was caught in the act, and astronomers around the world swung their telescopes to the coordinates it provided. The trail led to a blazar, a monstrous galaxy with a supermassive black hole at its core, shooting a jet of radiation and particles directly at Earth. This was a cosmic particle accelerator of almost unimaginable power, and it was finally confirmed as a source of these high-energy neutrinos. But blazars are not the only cosmic engines capable of such violence. Another source was found in a tidal disruption event, a star that wandered too close to a supermassive black hole and was violently shredded into a long, spiraling streamer. As the stellar debris crashes together and falls into the black hole, it creates a temporary, brilliant beacon and can launch particles to near light speed, producing neutrinos in the ensuing chaos. Each detection is a new thread in the cosmic web, connecting a tiny, almost undetectable particle on Earth to a cataclysm of stellar proportions millions of light years away. These ghost particles are our direct link to the universe's most extreme environments, offering a view of the cosmos that is completely unobscured by dust or distance. What other violent births will we trace back through the silent journeys of these cosmic phantoms? The ultimate fate of everything hangs on the nature of the very force that pushes the cosmos apart. Will our universe end with a whisper, a scream, or a cyclical rebirth? The leading theories all hinge on the subtle, unknown properties of dark energy. The most accepted forecast is the heat death or the big freeze. In this slow, cold finale, the universe continues expanding forever, accelerated by dark energy. Stars will eventually burn through their fuel, galaxies will fade to black, and black holes will evaporate over unimaginable eons. All energy will gradually spread out into an ever-thinning, lukewarm haze. The cosmos will reach a state of maximum entropy, a final equilibrium where no more work can be done, no stars can form, and no life can exist. It is an end not of fire, but of ice, a silent, eternal fading of all light and structure. Yet dark energy could have a more dramatic card to play. If its repulsive force grows stronger over time, it could lead to a far more violent demise known as the Big Rip. In this scenario, dark energy would eventually overcome every force that holds things together. First, it would tear apart galactic clusters, then individual galaxies. As the acceleration intensifies, it would rip stars from their galaxies and planets from their stars. In the final, terrifying moments, even atoms and atomic nuclei would be torn asunder, and space-time itself would be shredded into meaningless fragments. The very fabric of reality would be pulled apart at the seams. A third, more symmetrical possibility is the Big Crunch. This theory suggests that if the density of matter in the universe is high enough, or if dark energy somehow reverses its effect, gravity could eventually win the cosmic tug of war. The expansion would slow, halt, and then reverse. All of creation would begin rushing back together in a mirror image of the Big Bang. Galaxies would collide and merge, the temperature of the universe would soar, and everything would be compressed back into an ultra-hot, ultra-dense singularity, a potential seed for a new Big Bang and a new universe in an endless cosmic cycle. Which of these fates awaits us depends entirely on a number we do not yet know, the equation of state for dark energy. Is it a constant force, as Einstein's cosmological constant suggests, leading to the long freeze? Or is it a dynamic phantom energy that strengthens, dooming us to the rip? The answer is written in the invisible push that fills the vacuum, a final mystery that holds the last page of our cosmic story. From the silent birth of the cosmos to its ultimate, unknown fate, we have journeyed across 25 profound mysteries. We have witnessed the invisible hand of dark matter and felt the repulsive push of dark energy. We have listened for alien signals in the eerie quiet and chased interstellar visitors like Oumuamua. We have seen stars dim in inexplicable patterns and felt the spooky connection of entangled particles. We have stared into the information-devouring abyss of black holes and mapped the strange alignments in the universe's first light. We have found missing lithium from the dawn of time and traced ghostly neutrinos back to cosmic cataclysms. We have stood before the perfect geometry of dying stars and the hexagonal storm on a distant world, each one a question mark written across the sky. These are not just puzzles for scientists, they are a testament to the human spirit's unyielding drive to look into the darkness and ask why. We are a species born of stardust, gifted with consciousness, and compelled to seek our place in this vast, beautiful, and mysterious cosmos. Every one of these mysteries is an invitation, a frontier waiting for the next curious mind. So we turn the question to you. After this journey to the cosmic horizon, which of these 25 mysteries captures your imagination the most? Is it the phantom pull of the Great Attractor, the fleeting brilliance of a fast radio burst, or the chilling possibility of the Big Rip? Share your thoughts in the comments below, and if you are ready for more journeys to the edge of understanding, subscribe to continue exploring the greatest secrets of the universe.